A wave that travels from one medium to another can be transmitted or reflected, and this depends on the properties of the boundary separating the two media. So for example, if our medium 1 is a thinner string that has a lower mass compared to the string being medium 2. So recall that the wave speed in a string was equal to the square root of the tension force in the string on the mass per unit length of the string, being the linear density. So if m1 is smaller than m2, then the wave speed in medium 1 is going to be greater than that of medium 2. So considering this incident wave pulse propagating through string 1, then when it gets to the boundary, string 1 will exert a force on string 2, pulling it upwards. And by Newton's third law, that force is equal and opposite to the force exerted by string 2 on 1. Now because string 2 is heavier than string 1, so it has a higher inertial resistance, it's going to accelerate upwards by a small amount at the boundary compared to string 1. So consequently, the reflected wave is going to be flipped upside down when it moves back through string 1. And the transmitted wave is going to have a smaller amplitude compared to the incident wave. Now on the other hand, if string 1 is heavier than string 2, this means that the incident wave speed is lower than a transmitted wave speed. So in this case, when a wave pulse reaches the boundary, it'll exert a force on string 2. And let me move this a bit. And by Newton's third law, string 2 exerts an equal and opposite force on string 1. But because string 2 is lighter than string 1, so it has less inertial resistance, then it's going to accelerate upwards more than string 2 accelerates downwards. And consequently, the reflected wave pulse remains upward, but has a lower amplitude than the incident wave pulse when it's traveling backwards through the string. So recall the energy of a wave is proportional to the square of the amplitude. So because the transmitted wave has a higher speed, it has a higher kinetic energy, and therefore the reflected amplitude is lower than the incident amplitude. And note that the frequency of the wave does not change when it travels from one medium to another. And if you look at a simulation to make this more clear, if we have medium 1 having a lower density than medium 2, and we run a simulation, as expected, the heavier string is harder to pull upwards compared to the string with a lower density, so the reflected wave gets inverted. Now on the other hand, if we flip these scenarios, so we have a heavier string to a lighter string, and run a simulation, as expected, the reflected wave remains upright. And I'll link this simulation for you in the description so you can compare these results with the concepts that we just covered. Transverse waves, such as light waves, which have an electric field with an amplitude of E, and a magnetic field with an amplitude of B, oscillating in the perpendicular directions, to the direction of the propagation of the wave. And these fields oscillate perpendicular to each other. So these waves may be polarized if they are reflected from a surface, refracted through a medium, or pass through specific openings. And we view polarization in terms of the oscillation of the electric field, but noting the electric field is always accompanied by a perpendicular magnetic field. And polarized light has an electric field that oscillates in one plane. So if we consider this incident light beam being perpendicular to the wave front, which is traveling in a direction of the ray, then we can represent the oscillation of the electric field being perpendicular to the direction of propagation of the wave front using arrows like this. So the amplitude of the oscillation is from the midpoint to this point. And note that a beam of light is unpolarized in reality. So in this case, we'll consider an incident beam of light comprising waves with electric fields that oscillate perpendicular to each other. And they're also perpendicular to the direction that the wave propagates. So this orange electric field will oscillate in and out of the screen. So let's draw another arrow over here to show a few different positions of the wave front. Now when this light wave encounters a surface, it interacts with the molecules in which the electric dipoles change the direction of oscillation of the electric field. So for example, this component of the electric field cannot exist because it must be perpendicular to the direction of propagation of the reflected wave. So this gets cancelled, and what remains is the electric field that oscillates in and out of the screen. And therefore, the electric field of the reflected wave oscillates in one plane, and therefore unpolarized light gets fully polarized when reflected. Now when this light gets refracted, then it becomes partially polarized. So you get the electric field changing direction slightly, and you continue to have an electric field from the unpolarized light oscillating in and out of the screen. So because this refracted light wave is not oscillating in one plane, then it's not polarized. Now if we look at this scenario, where the incident light is going through a polarizer or a polarizing filter, and polarizers only allow light waves that are oscillating parallel to the axes of polarization. So schematically, we can see this as an opening. So consider light being emitted from this flashlight, which is unpolarized. So for example, it has light waves oscillating in the XY plane. So this may look something like this. And it has light waves oscillating in the XZ plane. So that's an example of unpolarized light. Though in reality, the waves are going to be oscillating in all sorts of directions, as long as the electric field and magnetic field are oscillating perpendicular to the direction of propagation of the wave. And note that here, we're only looking at the oscillation of the electric field. So it's implied that there's a magnetic field oscillating in a perpendicular direction. So as this beam of light passes through the opening, then this wave of light is oscillating in the parallel direction to the polarization axis. So therefore it's going to pass through the polarizer. But this wave, on the other hand, is oscillating in the direction that's perpendicular to the axis of polarization, so it's not going to pass through the polarizer. So therefore, the light that passed through this polarizer has been polarized, because the light wave that made it through the polarizer is oscillating in a single plane. So when this light wave travels through the second polarizer, where the polarization axis of this second polarizer is in this direction, the direction of oscillation of this wave is perpendicular to the polarization axis, and therefore this wave is not going to pass through the polarizer. But note that if this opening was oblique like this, then part of this wave will pass through the polarizer. And we'll see this more clearly in a simulation. And I'll link this for you in the description so you can practice. So here we have unpolarized light, where the electric fields, due to the different waves in a light beam, are oscillating in different directions. So when the light goes through this first polarizer, we can see that it's oscillating parallel to the axis of polarization. And when it encounters this polarizer, if we change the angle of the polarization axis, you can see that the component of the wave that's parallel to the polarization axis passes through. And if the polarization axis is perpendicular to the plane of oscillation of the wave, then the wave doesn't go through. So have some practice and think about this. And note that longitudinal waves cannot be polarized. The intensity of a light wave is defined as the energy of the light wave transferred per unit area per unit time. And the energy transferred per unit time is equal to the power, and therefore the intensity can be written as the power on the area. Now, given that the energy of the light wave is proportional to the square of the amplitude of oscillation of the electric field, if we suppose this is our axis of polarization, and a light wave from this light beam is oscillating in the plane parallel to the following axes. So the amplitude of the oscillation is measured from the middle and is initially E0. And if we resolve this electric field in the direction of the axis of polarization, so the other component is perpendicular to the axis of polarization, so the amplitude of the electric field after polarization is equal to E0 multiplied by the cosine of this angle, being the polarization angle. And if we square both sides, because we recognize that the energy of the light wave is proportional to the square of the amplitude of the electric field, and therefore the intensity of the light wave is also proportional to E squared, we can write this relationship as the intensity of the light wave after polarization is equal to the initial intensity of the light wave by the cosine of the polarization angle squared. And this is Malus's law. And therefore we see the intensity of the light wave gets reduced when the electric field is oscillating at an angle to the polarization axis. And if the electric field of the wave is oscillating perpendicular to the polarization axis, theta is equal to pi on 2, and the intensity after polarization is thereby 0. So note that a light beam comprises different waves oscillating in different planes, so the angle between the oscillating electric field and the axis of polarization varies from 0 to pi on 2. So therefore the average intensity of the light wave, noting that the amplitudes of oscillation of the electric fields in a light beam are the same, so their intensities are also equal, is equal to I naught cosine squared 0 degrees plus I naught cosine squared 90 degrees on 2. So on average, the intensity of a wave that gets polarized is reduced by a half.